Now we're going to get into hurricane prediction. We've already talked about the structure of the storm. Now we want to know where the storm's going to go. When we talk about the storm, you know basically about the progression, so you can get an idea of the timeline of the prediction, and that timeline follows the stages of development from a tropical wave or disturbance and that converging air that you saw on the east side of the frontal wave. That's the tropical disturbance. It can start to form its cyclonic nature in a tropical depression where the winds are about 30 to 40 miles an hour, 20 to 34 knots. Tropical storms, you know well. One of them just came in a few weeks ago. And then hurricanes with winds that are in excess of 70 miles an hour and can go up to 175, 190 miles an hour, sometimes over 200. So you can look at prediction in terms of stages in development. We want to look at prediction geographically. But before we even get there, well, I just went over the stages, the Saffir-Simpson stages of the hurricane scale, that those hurricanes can move from even a scale of 0 to 5. And the scale of 0 is winds that are right around 70 miles an hour, then 1 when you go up by about 5 miles an hour, and you go up in stages up to winds in excess of 150 miles an hour. They can go up to 200 miles an hour, catastrophic damage. That's the scale. You have heard of the scale. We're going to be talking about flooding as a real challenge rather than winds. So I think that flooding is the undervalued danger, and so that's what we're going to be talking about. And you can look over these if they're cut off a bit on the PDF, but we're talking about a category 1 storm to a category 5 storm in terms of flooding rather than wind. And the tidal rise of the category 1 storms can be about 4 feet. The tidal rise of a category 5 storm can go right to about 20 feet or more, covering the first floor of a house, therefore undermining that, sending people to the rafters and to the attics, but you can easily have that house moved away. So that's where I'm going to concentrate on the flooding. And in terms of geographically predicting that flooding, that tracking that storm is tough to do. These are paths for years of storms. So you see that very basically these storms will evolve off of Africa, and they will follow the intertropical convergence zone, that low pressure area, until they start to veer off. And they start to veer off. Oh, look, they start to veer off, moving to the right as you get into the mid latitudes with the Coriolis effect, with the Gulf Stream effect, with the prevailing westerlies as well. So this is where you get into craziness of where these storms go. Do they stay farther east? Do they stay farther west into the Gulf? How do we predict that? There's actually some ways to do that. When you are looking at these storms and you are looking at them toward the beginning of hurricane season in August. Hurricane season starts in July. But let's look at the beginning. We can look at August, September. We'll get into October in a second. When you look into that, you are really being steered by the Bermuda High, which during the summer season in the Northern Hemisphere is over Bermuda. And so this steering high will steer the low pressure and push it away. Remember, high pressure pushes low pressure. So that in many cases in August, these have a really predictable pattern in August. The warm air in the Caribbean is not as warm in August. And so these storms have a predictable pattern up the coast. They may not be as devastating because the heat engine isn't completely in place because of that specific heat of water is not charged up effectively yet. And that Bermuda High is sitting right on top of Bermuda. Come September, things start to change. Remember, September is when the equinox comes into line and the seasons are starting to change over. When those seasons start to change over, that Bermuda High migrates. And that Bermuda High migrates over to the Azores in this area. As this Bermuda High moves over to the Azores, those Azores are completely clear, but that high is missing from the Atlantic, so these storms do not have as much of a steering mechanism in place, and these storms can start to really come out east, which protects the East Coast in many ways. But in September, the water is so much warmer that if that movement of the Bermuda High is delayed, you could have a ferocious storm come through the East Coast as a result of that. Now you know a little bit more about the oscillations that move that Bermuda High on a routine basis over, but that can leave the East Coast exposed if that Bermuda High does not move as quickly as it does in other years. So look into that a bit more. Fascinating stuff to track the Bermuda High. Look at October. By October, that Bermuda High is really moving over toward the Azores a bit more. That's where it spends its northern hemisphere winter. And that's why Europe kind of clears out to go to the islands in this area, because it stays so much warmer and drier during the winter. But in this case, you will have storms in October that are more likely to be out in the Atlantic and maybe less likely to hit the East Coast, as September is a big month for hurricanes. October, less of a big month, but there can still be devastating storms. It all moves with the Bermuda High. I wanted to show you some October storms and the craziness that ensues when that Bermuda High is gone. You can see the nutso tracks that some of these storms can take without the steering high of the Bermuda High. And I wanted to show you too, and include in, we're not just talking the East Coast here, we're also talking the West Coast. The Pacific storms are driven by the same sorts of frontal waves, and they can move in and pick up and produce the Arizona monsoons during July, August, September. So this provides moisture into the desert areas of the Pacific. Very important to Phoenix, Arizona. If you were out at the University of Arizona, where a lot of my work is out of, you would the Arizona monsoon is so important to their weather climate. Talking about prediction and storm surge and flooding and where it happens, the highest winds and the most flooding is going to be on the right side of the storm as it's traveling. This is an important point that most people never grasp. So when they look at those cone predictions, they're just looking right in the middle of that cone. Oh, am I in the middle? No, I'm not in the middle. So I don't have to worry about evacuation. If you look at those cones, look at the right side of the cone, because the right side is going to get slammed. And as a result of that, that was Sandy for us. But in terms of the specifics of how to look at this, let's look at a very potent storm in 1938, which really drove our ability to predict these storms better. This is before radar. This is before radio sondes and soundings. This is before satellites. And look at what happened off of the coast of Long Island. This is called the 1938 storm. It didn't even have a name to it, but it was clearly a hurricane. And what we notice is this. This is what came in as observations, as data. Then we work the calculations off the data and produce the analysis, right? So we're going back to the scientific method here. When it came in as data, the fishermen on the East Coast that were off of the South Montauk area were reporting in winds of 185 miles an hour on their fishing boats. I mean, it sunk many boats. The people that could ride it out were reporting these ferocious winds. And look over here. The people who were riding this storm out off of the area that was closer to New York City, closer to Rockville Center, were reporting winds of 45 miles an hour. What are you doing with winds of 185? What's going on here? And then we started to be able to calculate and analyze the difference in those winds and what was happening. This storm was moving from south to north at 70 miles an hour. And that was well documented, that 70 mile an hour movement of the storm. And there were counterclockwise winds, rotational winds, that were moving at 115 miles an hour in a rotation. That 70 miles an hour movement of the entire storm plus the counterclockwise winds at 115 gave those fishermen their observation of 185 mile an hour winds on the right side of the storm, the direction of the storm on the right side. You can see from that ferocious wind at 185 that you would be pushing air and water to the south coast of Long Island, to that Montauk area at a very forceful pace, pushing that water onto that area and surging that water and flooding this South Fork of Long Island, and just submerging it. So the right-hand side of the storm gets the brunt of the push and the surge and the flooding. Conversely, on the left-hand side of the storm, very different picture, and the result of this is that there's complacency, because I only saw 45 mile an hour winds. I don't know what you're talking about with 185 mile an hour winds. Let's analyze what they were talking about with the 45 mile an hour winds. This storm was moving from south to north at 70 miles an hour. And this storm had counterclockwise rotational winds at 115 miles an hour. So this is 70 miles an hour from south to north, plus negative winds north to south of 115, leaving a net of 45 mile an hour winds that were moving from south to north. That's the difference that these fishermen noted on the left side of the storm. That's why when you don't understand this, you get complacent. I'm going to ride this storm out. It's not going to be a big deal. Not understanding that the right side of that cone is the real area. If you want to look into good work, figure out how to explain to people that these cones really have the depth side on the right side of the cone. That is a graphics need that NOAA knows all too well. They don't broadcast these warnings in a fashion that people can relate to. You can practice this yourself in terms of practicing the right side of the storm and the observational winds. This storm is moving from south to north at 25 knots. It has counterclockwise rotational winds at 100 knots. So that when you are on the right side of the storm, you are adding 25 knots plus the 100 knots of the rotation to get an observation of winds at 125 knots. Now you look at the left side of the storm and you figure out why it's at 75 knots. Remember, you have 25 knot winds moving from south to north, and you have 100 knot winds moving from north to south. So do the subtraction and figure out why you come up on the left side of the storm with observational winds at 75 knots. It's a good exercise. Hope you can do it, and I'll see you on the other side.